Namaste, my dear children. In this class, you learn about pressure in fluid. Basically, you know very well, gases and liquids are called fluid. So, the fluid exerts a pressure in the surface of the liquid as well as the walls of the liquid container also. Let us see the class.
Take a water bottle, and I put some color over there so we can see that water, and punch two holes in that bottle, one at the top and one at the bottom. And then you see that the water squirts out, but the water at the bottom will come out at a much higher speed compared to the water at the top. And that's why it's falling much farther away. But why do you think that's happening? Well, it turns out it's the same reason why when a submarine dives very deep into the ocean, it can get crushed by the water. So to figure out why these things happen, we need to talk about pressure inside liquids. And that's what we will do in this video. So let's imagine we have a container filled with liquid. Let's say it's water. Now, you know what helps me when it comes to thinking about pressure inside liquids? I like to imagine that this liquid is made of tiny cubes stacked on top of each other. So if this is water, then we can imagine these are tiny cubes of water sitting on top of each other. Why? Because now I can compare this to a stack of water balloons sitting on top of each other. And once we understand, what's happening to pressure over here, we can relate that to over here and understand the pressure. So let's think about this. So if we look at a water balloon which is somewhere at the top, let's say this one, then because there is one balloon on top of it, this balloon is being pressed down with a force of, or with the weight of one balloon. Now, because of this weight, why doesn't the balloon just fall down? Hey, that's because there is another balloon below it, which supports the weight, which pushes it up, trying to balance this force. This is very similar to when you're standing on a floor. Why doesn't gravity pull you through the floor? Because the floor pushes up on you, making sure that the forces on you are balanced, right? Now, of course, you might see that the force from the bottom is a little bigger than the force from the top. And the reason for that is because this supporting force not only has to balance the weight of this balloon, which is this force, but it also has to balance the weight of this balloon, right? And that's why the supporting force has to be a little bit more than this. But don't worry too much about that. Now, the same thing can be said about these two balloons as well. So all these balloons are being pressed from the top and from the bottom with little forces. However, if you now look at a balloon which is somewhere at the bottom, let's say this one, look at how much weight is pressing down on it. That's a lot of weight, right? So it's being pressed down with a humongous force, much bigger compared to this one. And similarly, it is also being supported up with a lot of force. And the same thing can be said about these balloons as well. And so you can see as you go down through this stack, the pressure on each balloon starts increasing. And the reason we use the word pressure is because, notice on each balloon, the net force is always zero, right? All the forces are balanced, and that's why the balloons are not moving or anything. They're all at rest. Although the forces are balanced, they are being pressed, right? And that's why we use the word pressure. And how do we calculate pressure? Remember, we calculate pressure as force divided by area. So over here, the force per area is pretty small. But as you go down, notice the force acting over a tiny area, that starts increasing. And so as you go down, because of the weight, the pressure starts increasing. And the same thing is going to happen here as well. If you look at some water cubes which are at the top, since they're not carrying much weight, they're being pressed with little amount of pressure. But as you go down, for example, look at these cubes, they are carrying a lot of weight on top of them, right? So they're being crushed by humongous pressure. And that's why in liquids, as you go down with depth, the pressure increases. But horizontally, notice the pressure remains the same. Horizontally, the pressure remains the same. It's with the depth pressure increases. And this now can help us explain why submarines get crushed if they go too deep. So if we have a submarine somewhere at the top, then it's being pressed with little pressure. So the amount of force acting per unit area on this metal is pretty small. The metal can handle it, no problem. But as the submarine dives deeper and deeper, it starts carrying more and more weight of liquid on top of it. Eventually, when it dives too deep, the amount of force over unit area on that metallic body becomes extremely high. It now starts getting crushed under the pressure of the water, and as a result, eventually the metal cannot handle it and the whole submarine can get crushed. All right. Now, how does this explain why water comes out at the bottom with more speed compared to the top? Why is this happening? Well, the reason for this is because liquids also push on the walls of the container. Again, to understand why, let's look at the balloons. If you look at the balloons carefully, we see because as you go down, the balloons are being squeezed more and more, they also tend to deform more and more. Because liquids can easily flow, the balloons tend to get more and more deformed, right? Now imagine what would have happened if we were to put walls trying to contain all those balloons within the walls. What would happen? Well, at the bottom, the balloon will not go through the wall, of course. They will not go out of the wall like that, but they will push on the wall. Can you see that? They will start pushing on the wall because they want to get deformed. As a result, you can see right at the bottom, they will start pushing on the wall with a lot of force because they tend to get deformed a lot. So since the balloons at the bottom are squeezed a lot, they tend to deform a lot, and they will start pushing horizontally on their neighbors and also on the walls of the container. But if you look at the balloons at the top, they're not squeezed much. And so they don't try to deform much. And so they will only push with a little force on their neighbors and on the walls of the container. And so from this, can you see that because of this squeezing effect, balloons not only put pressure in the vertical direction, but because they tend to deform, they automatically start putting pressure in the horizontal direction as well. They start pressing each other horizontally as well. And even this pressure, you can see, starts increasing with depth. And the same thing's going to happen here as well. If you look at the water cubes over here, since they are being pressed a little bit, these water cubes tend to flow a lot, not a lot, sorry, a little bit. And so they will start pressing on each other horizontally, little bit, even on the walls of the container. But since these water cubes are being squeezed a lot, they're being crushed a lot, they will tend to flow a lot. They'll tend to deform a lot like these balloons. And so they will start pushing on each other horizontally a lot, and even on the walls of the container. And so now if you look at the force acting per unit area at the walls over here, notice even that starts increasing as you go down. And so you can see liquids push on the walls, and even this pressure starts increasing as you go down. And this is the unique thing about liquids. Solids, for example, wouldn't do this. I mean, if these were, like, say, wooden boxes stacked on top of each other, wooden boxes will not try to deform, and they wouldn't put pressure horizontally. But liquids do. That's the difference. And because of this, now we can understand what will happen if you punch a hole over here and punch a hole over here. Well, because the pressure horizontally is a lot, the water will try to come out with a lot of speed. But over here, since the pressure is less, the water will come out with less speed. And there's another practical application of this, which can be seen in the construction of dams. Have you seen that the base of the dams are very wide? Why? Hey, because of the same reason. You see, because we saw that water starts putting more pressure on the walls at the bottom, same thing's gonna happen here. This water will start pushing more on the bottom, more pressure on the bottom. And so to withstand that pressure, we need a wider base over here. And that's the story of pressure in liquids. So let's get rid of all these extra arrow marks and quickly summarize what we learned in this video. So we learned in liquids, because they have a tendency to flow, they put pressure in all the directions, not only in the vertical, but also in the horizontal, also on the walls of the container. And we saw because as you go down, they have to carry more and more weight, this pressure starts increasing with depth, but the pressure remains the same horizontally.
In the last